Okay, paper 1. Using the bond enthalpy values given, we're going to calculate the enthalpy change for the reaction. So we know that we should calculate the enthalpy change this way by adding up the sum of all the bonds breaking, and then we'll subtract the bonds that we're forming. We do it in this order because the negative sign makes the values negative. The bond enthalpy value is negative, which is exothermic, which is what we associate with bond forming, where the values will be positive for the bonds that we're breaking. So we have to draw out the structures. HI really has to be this. Again, no one's going to mark your Lewis structures on paper 1, but it's helpful to draw them out. I'm going to ignore lone pairs for now. I just care about the bonds. And so the bonds that we're breaking are H to H and I to I. Those values are 440 and 150 for a total of 590. And then the bonds that we're forming is 2 times 300, because there's 2 in front of the HI. So we're getting out 600, and so I can see that the change will be minus 10. Whoa! There, it's back. Okay, so the first answer should be C. Okay, which equation represents the bond enthalpy for the H to Br bond? Well, the definition of a bond enthalpy is the enthalpy change when we break 1 mole of a bond in the gas phase. So anything with liquid, we're going to cancel out. And anything that shows bonds reforming in the product, like Br2, when it says Br2, that means that Br is bonded to Br, and the half just means there's a half mole. So we don't want to reform any bonds as part of our definition. That's not what's measured when they measure a bond enthalpy. So really the only one that fits is this one. It shows everything in the gas phase, and it shows the bond between H and Br breaking apart. Specific heat capacity, the C value for water, right, that's 4.18. The units has to do with the energy per mass per degree. So how much energy does it take to heat up a mass of something by a certain amount of temperature, or particularly to heat it up by 1 degree Celsius or 1 Kelvin. So the units are here. That's the energy per kilogram per Kelvin. And those minus ones mean that they're in the denominator. So it's the energy per mass per temperature change. That's why D is the best answer. Given the enthalpy change for the reaction below, right, so you can see they've given it here, which statement is correct? So now these ones we haven't, okay, I'm going to skip 4 because I realize at this point we may not have actually we haven't introduced formation yet. So I'm going to skip question 4. Okay, we'll come back to it. That's not a hard question if you know what the enthalpy changes are. Question 5, which is the best definition of standard state? I'm going to skip that one as well. We'll talk about that more when we talk about formations. 6, consider the following enthalpy of combustion data. What is the enthalpy of formation of ethane? Now they've given us this equation. So we haven't done enthalpy of formation yet. However, given this equation, we can use the other equations to solve for it. We practiced that in class. So remember, just get you're looking at these 3, the carbon, the hydrogen, and the ethane, the C2H6. We need to get them in the right position and with the right coefficient in the equations up above. So I see here that I have 2 carbons on the left in the final equation I'm trying to solve for. So I need to go back up to these other equations and make sure that I have 2 carbons on the left-hand side as a reactant. I see that carbon is here, so it's on the correct side, it's in the reactants, but I need to double everything. So 2, and that would be a 2, and that would be a 2 here, and that makes minus 2x. Okay, so I've done carbon. Then I would go into hydrogen. I need 3 of it on the left. I can see the only place with hydrogen is here. I need to multiply this by 3. That would become 3 halves and 3 waters, and I get minus 3y as the change. And then for the last one, I see that this C2H6, I need it on the right-hand side as a product. I can see here it's on the reactant side. That means I need to reverse this whole equation, which means I'm going to reverse Z, or Z. Now, if this were paper 2 and we really wanted to be careful, I might go through and actually see how the oxygens add up and cancel out. How do the other things cancel out? But to be honest, usually I don't do that. I know This is the only place that carbon is in these reactions up above. This is the only place where hydrogen is, and this is the only place where ethane is. So in this kind of example, if I can get those three things into the right position, everything else really has to work itself out. So these values are the ones I'm going to use to get the correct final answer. So I need minus 2x, I need minus 3y, and I need positive z. And the one that looks like that to me is C. Okay, 7 is a good sort of conceptual question to think through. Okay, two different experiments, A and B. A solution of sodium hydroxide is added to a solution of hydrochloric acid. The initial temperature of each is 25. I can see that I'm adding the same volume and the same concentration, NaOH, and based on N equals CV, that means both of these I'm adding the same amount of moles of sodium hydroxide. For this other one though, this one I'm adding it to 50 centimeters cubed of HCl, and this one I'm adding it to 100 cm cubed of HCl. Now, probably useful information to know, and I don't expect you to know this equation for the time being, is that NaOH and HCl react 1 to 1. So that means that their mole ratio is 1 to 1. Now I can see on the left-hand side I'm using 50 of 1 molar and 50 of 1 molar. So in this case, the moles are equal of NaOH and HCl. In this other one, I can see in this one I have 50 cm cubed of 1 molar, and this one I have 100 cm cubed of 1 molar. So in this instance, I have 2 times the moles of HCl than I do my moles of NaOH. Now what that means is that the NaOH is the limiting reactant, and the HCl is in vast excess because we have twice as much of it as we have of NaOH. So what that means is adding all this extra HCl actually doesn't increase the amount of energy that you're going to release. The amount of NaOH is the same in both situations, and in both reactions, in both situations, it's the limiting reactant. So when we do that delta H calculation, right, and we think about negative Q over N, remember the moles on the bottom is the moles of the limiting reactant, not the combined moles of both reactants. So since in both these situations, I'm going to have the same moles of NaOH limiting me, in both situations, I'm going to release the same amount of energy. So same heat released in experiment A and experiment B. That's the important conceptual idea to have to figure out the answer to this question. Because you're adding the same amount of sodium hydroxide in both, that will limit how much heat gets released. So both of them have the same amount of heat released. But in the experiment on the left, you have a total volume of 100 centimeters cubed. And in the one on the right, you have a total volume of 150 cm cubed. So that means if you take the same amount of heat and you try to heat up more water with that same amount of heat, the temperature change will be smaller. So on the one on the right, we're going to have a lower final temp because we're heating up more liquid with the same amount of heat. So the first important concept is that it's the same amount of heat being released, and I know that because it's the same moles of limiting reactant, but they have a different amount of mass to heat up, right? In the Q equation, it's mc delta T, so the thing that's different is the M. We are heating up 100 grams in the one on the left and 150 in the one on the right. So we'll have a smaller temperature change in the one on the right because we're heating up more liquid with the same amount of heat. So in terms of correct answer, the highest recorded temperature of experiment A is lower than the highest recorded in B. That's wrong. The one in A would be higher. The highest recorded temperature of both is equal. Wrong. The heat produced in A is lower. Wrong. The heat produced in both is equal. D is the best answer. Okay, they're doing a calorimetry question here, but they have not solved it, so we just have to figure out where everything goes. We know delta H is negative mc delta T over N. Okay, and then we may have to break down those further. They mix 1 gram of sodium hydroxide with 99 grams of water. So this is one of those ones being done in aqueous solution. So we're adding things into the liquid. So to me, that means the total mass that we're trying to heat up is 100 grams. So I'm going to plug that in for M. Now they also said, okay, sorry, I'm getting ahead of myself. The C value, 4.18. They give us that later. The temperature increase is 18 to 20.5. That's a 2.5 degree increase. And they say which expression gives the heat evolved in kilojoules per mole. So that is a reminder that I need to do per mole. Now they've included that word evolved. That means that's the same thing as like released. So I don't really need to bother with the negative sign. I can see none of these have a negative sign in front of them. So I can kind of ignore that. They've implied that the energy is being released and that it's exothermic. Okay, so I've got my Q expression on the top. And on the bottom, I need to have my mole expression. It's based on the moles of limiting reactant. The only thing that they've given me here is that I'm adding sodium hydroxide to the water. So I'm dissolving the sodium hydroxide. So the moles must come from the mass of sodium hydroxide. So N equals mass divided by molar mass. So if over here, I would think it's 1 gram, the molar mass of NaOH, if we add it up, is 40 grams per mole. Okay, well, if I divide something by a fraction, it's the same as multiplying by the reciprocal. So remember, I'm not actually solving this, I just have to set it up properly. The 40 is going to end up here on the top. The 1 remains on the bottom. And I think they're just not going to show the 1. You can see in the choices on the left, none of them show a 1. So the 1 is here. The last thing that we need to do is they want us to solve kilojoules per mole. And we need to remember that since we're using grams, right now the answer would come out in joules per mole. So I need to divide this answer by 1,000. That's the conversion of joules to kilojoules. So now I'm looking for an answer. They're not going to show this 1 that looks like this, and C is the best answer. Okay, a couple more using the equations below. Okay, we can solve for this delta H, and we've got, again, trying to find these 3 pieces, getting them into the right positions. So C is on the left already with one of it. H2, there's 2 H2. So I need to multiply this equation by 2, and in this one I'm going to get really sloppy, and I'm not even going to multiply through the coefficients. I'm just going to do that. That gives me minus 572, I think. Yep. Okay, and here CH4 is on the right-hand side. That means here I need to reverse this equation, so that becomes positive 890. Okay, and then through a little bit of math, get minus 962, and I get positive 890, and the difference is minus 72. Okay, 5. A 5 gram sample of a substance was heated from 25 to 35 using 2 times 10 to the 2 joules. That's the same as 200 joules. What's the specific heat capacity? So this is one where we're solving for C. I can do that in advance. I get 200 joules, I get 5 as my mass, and I get 10 down here. So I've got 200 divided by 50, and that equals 4. Okay, and I think we'll call it at 1 to 10. We'll do a separate video for the paper 2 questions.